There are worlds in the Milky Way that never see a sunrise. They do not circle a star. No familiar dawn moves across their horizons. No summer begins because an orbit has carried them closer to a source of light. They travel instead through the spaces between stellar systems, following long paths shaped by the gravity of the galaxy itself. Astronomers often call them rogue planets, though the name can suggest more certainty than the science allows. Some may have formed around stars and later been thrown away during the crowded early years of a planetary system. Others may have formed on their own from collapsing clouds of gas and dust, more like very small stars that never became stars at all. In both cases, the result is a planetary mass body moving without a parent sun. Most of these worlds are difficult to see. A mature planet does not produce visible light in the way a star does, and after billions of years, its surface may radiate only a faint trace of heat. Against the background of the galaxy, such an object can pass through a telescope's field without leaving a recognizable point of light. Yet, gravity does not need a world to shine. When a wandering planet passes almost exactly between Earth and a more distant star, its gravity bends and concentrates some of that star's light. For a brief time, the background star appears brighter. The event may last only hours or days, depending on the mass and motion of the unseen object. This effect, known as gravitational microlensing, has become the most powerful way to search for low-mass worlds that cannot be found by ordinary planetary methods. The usual techniques for discovering planets depend on a host star. A planet may pull its star back and forth, or cross the star's face and slightly reduce its brightness. A world with no star provides neither signal. It has no regular transit to repeat, no stellar spectrum to disturb, and no orbit that can be watched returning year after year. Microlensing gives astronomers one chance. The alignment forms, the distant star brightens, and then the geometry moves on. In many cases, the event will never repeat. The planet continues through the galaxy, while the background star returns to its former appearance as though nothing had crossed the line of sight. This makes the population difficult to count. Astronomers have detected candidates and groups of young, free-floating planetary mass objects, but the total number in the Milky Way remains uncertain. Some studies suggest that low-mass wanderers may be common. Other observations remind us how difficult it is to distinguish a truly unbound planet from one traveling on an extremely wide orbit around a faint and distant star. So the story begins with an absence rather than an image. There is no bright disk to place at the center of the scene. There is no star to define the calendar, no illuminated side to separate day from night, and no simple way to know where one of these planets has come from. What remains is motion, gravity, stored heat, and a history written into a body that may have been traveling alone for billions of years. Tonight, we will follow that history from the crowded birthplaces of planetary systems into the open regions between the stars. We will look at how worlds can be released, how they cool, what may survive beneath their surfaces, and how a passing alignment can reveal an object that gives off almost no light of its own. Somewhere beyond the solar system, one of those worlds may be moving now between one star and the next. It does not need a sunrise to keep going. A wandering planet does not begin by wandering. Most planets are born in company. They gather inside broad disks of gas and dust, turning around young stars in regions where collisions are frequent and the architecture of a future system has not yet settled. Dust grains meet and cling. Larger fragments form. Over time, gravity begins to gather material more effectively, building bodies that may become moons, asteroids, rocky planets, or the dense cores of gas giants. From a distance, this process can look orderly. A flat disk surrounds a new star, and planets emerge along paths that seem prepared for them. Up close, the early years are far less stable. Young planetary systems can contain more large bodies than they will keep. Their orbits may cross. Their gravitational pulls can exchange energy in ways that slowly reshape the entire system. A planet that begins near its star may move outward, another may fall inward. Smaller worlds can be scattered into long elliptical paths, while larger planets shift only slightly and absorb most of the system's momentum. The changes do not always happen in a single dramatic encounter. A planet may pass a giant companion again and again, each meeting altering its orbit by a small amount. The path stretches farther from the star. The planet returns. Another close approach follows. Eventually, the orbit may open so widely that the star can no longer hold the planet at all. At that point, the world is not destroyed. It simply leaves. The same gravity that once kept it in orbit has transferred enough energy to carry it beyond the system's boundary. The planet moves outward through the distant debris that surrounds its former star, crossing regions where comets may still be loosely bound. The star grows smaller behind it. Its light weakens. The orbit does not curve back. For the first time, the planet has no year. This kind of gravitational scattering is one of the main ways astronomers think rogue planets are produced. Computer models of young systems show that when several massive planets form close enough to disturb one another, some can be driven into unstable paths. The system may settle only after one or more bodies have been removed. The survivors can remain in altered orbits around the star. The missing worlds continue elsewhere. Our own solar systems may have passed through a milder version of this restless phase. The giant planets appear to have migrated from the places where they first formed, and their changing gravitational relationships helped rearrange smaller bodies. Across the outer solar system, some models suggest that an additional giant planet could once have existed and later been expelled, though this remains a proposed explanation rather than a confirmed chapter of solar system history. The idea matters because it shows how difficult it can be to reconstruct what a mature planetary system once contained. A quiet system is not proof of a quiet beginning. The planets that remain reveal only part of the story. Other bodies may have fallen into the star, collided, broken apart, or been sent into interstellar space. By the time astronomers observe an older star, the evidence of those losses may be faint. Ejection can also happen when another star passes nearby. Stars are often born in groups within clouds that produce dozens, hundreds, or thousands of young suns. In those early clusters, neighboring systems can pass much closer to one another than stars usually do in the region around our sun today. A passing star can pull on distant planets, weaken their orbits, or disturb the balance among worlds already circling their own star. A planet far from its sun is especially vulnerable. Its orbital speed is lower, and the star's gravitational hold is weaker. A passing stellar companion may not need to come close to the planet itself. It only needs to change the surrounding gravitational landscape enough for the orbit to loosen. Binary star systems provide another route. When two stars orbit one another, planets can occupy stable regions, but the available paths depend on the star's masses, separation, and orbital shape. Some planets may circle one member of the pair. Others may orbit both stars from farther away. If the stars move closer together, exchange material, or encounter another star, planetary orbits can become unstable. Across millions of years, worlds can be transferred, scattered, or released, yet not every isolated planetary mass object must have begun around a star. Some may form directly from collapsing pockets of gas through a process resembling star formation on a smaller scale. A cloud fragment gathers under its own gravity, but never becomes massive enough to sustain ordinary hydrogen fusion. The result can be a brown dwarf, or at still lower masses, an object that resembles a giant planet. This creates a boundary that nature does not always draw as clearly as human categories do. Astronomers can define a planet by its mass. They can define it by its origin. They can define it by whether it orbits a star. Each method produces difficult cases. An object with several times the mass of Jupiter may have formed inside a planetary disk and later been ejected. Another object with the same mass may have formed directly from a collapsing cloud. They could appear nearly identical through a telescope, yet their histories would be different. For a distant, solitary world, origin can be harder to determine than composition. Young objects still carry heat from their formation. That warmth can make them visible in infrared light, especially when they belong to nearby stellar associations whose ages are known. Astronomers can compare their motion across the sky with the movement of young stars in the same group. If the object travels with them, it may have formed in the same region, but shared motion does not always reveal whether it began in a disk or in the cloud itself. Older wanderers are harder to trace. After traveling through the galaxy for hundreds of millions or billions of years, they may be far from the systems that released them. Their original stars have moved as well, orbiting the Milky Way along their own paths. The distance between a planet and its birthplace can grow until the relationship is almost impossible to recover. A world ejected early in its history may spend nearly its entire existence alone. It may pass through spiral arms, move above and below the galaxy's disk, and travel near stars that did not exist when its journey began. Most encounters will be distant. Space between stars is so large that even a galaxy filled with wandering planets would leave each one with immense room around it. The word rogue can make these worlds sound disruptive, as though they move against the structure of the galaxy. In reality, they follow gravity as faithfully as every star. Once released from a planetary system, a wandering world begins to orbit the center of the Milky Way. Its path becomes part of the galaxy's broader motion, shaped by stars, gas, dark matter, and the changing gravitational pull of structures too large to perceive from any one location. It has lost its sun, but not its place in the cosmos, and somewhere within its cooling interior, the conditions of its birth continue traveling with it. The first change would be light. A planet leaving its star does not cross a single border where day suddenly ends. The star recedes by degrees. Its disk becomes smaller. The energy reaching the upper atmosphere falls with the square of the growing distance, so each outward step removes more warmth than the last. What had once been noon becomes a pale illumination. Later, the star is only the brightest point in a sky filled with other points. For a world like Earth, sunlight supplies almost all the energy that keeps the surface temperate. Remove that input, and the balance begins to shift at once. The planet continues radiating heat into space, but the star no longer replaces what is lost. Oceans cool from above, weather changes. Water vapor falls from the atmosphere as snow and ice. The familiar circulation of winds and clouds weakens as the difference between warm regions and cold regions becomes smaller. The transformation would not be instantaneous. Rock, water, and atmosphere can store heat. A deep ocean releases energy over time. A thick atmosphere can slow the escape of infrared radiation. Volcanoes, radioactive elements, and the compression of material inside the planet continue to provide energy from below. For a while, the surface remembers its star. That memory fades unevenly. A small rocky world loses heat faster than a larger one because it has more surface area in proportion to its volume. A massive planet can hold internal warmth for much longer. A gas giant may continue glowing in infrared light after visible sunlight has become irrelevant. Jupiter, even while orbiting our sun, radiates more energy than it receives from sunlight. Much of that output comes from its gradual cooling and contraction, a process that has continued since the planet formed. A giant world cast into interstellar space, would therefore not become thermally inactive. Its upper clouds would grow colder, but deeper layers could remain warm for billions of years. Pressure would rise with depth. Hydrogen would change behavior. Heat would move upward from the interior and escape in wavelengths that human eyes cannot see. From nearby, such a planet might not look black. A young rogue giant could emit enough infrared radiation to be detected directly, especially if it formed recently and still carries the heat of its beginning. Invisible light, however, it would have little to reflect. There would be no bright crescent, no full phase, and no blue daylight scattered through an atmosphere. Any glow would come from within, faint and red, beyond the range of ordinary sight. A rocky planet would follow a different path. If it had oceans, their surfaces would begin to freeze. Ice would spread until the upper layers formed a global shell. Yet ice is not merely a sign of cold, it is also an insulator. Once a thick, frozen cover formed, it could reduce the rate at which heat escaped from liquid water below. Whether an ocean could remain beneath that shell would depend on many things: the planet's size, the depth of its water, the abundance of heat-producing elements, the age of the world, and the pressure created by the overlying ice. On some worlds, the ocean might eventually freeze almost completely. On others, internal heat could preserve liquid layers for long periods. This possibility is not unique to wandering planets. Several icy moons in our own solar system are believed to hold oceans beneath frozen exteriors. They receive little surface warmth from the sun compared with Earth, but internal heating and insulation can maintain liquid water below. Some are warmed by tidal flexing as they orbit giant planets. A solitary world would lose that source unless it retained a moon or another companion, but radioactive decay and leftover formation heat would still remain. A rogue planet could also carry a thick atmosphere into the dark between stars. If that atmosphere were dominated by hydrogen, it might trap outgoing infrared radiation more effectively than a thin atmosphere like Earth's. Under some modeled conditions, enough hydrogen could keep a surface or subsurface ocean from freezing even without starlight. This remains a theoretical possibility, not a description of a known world. No isolated planet with such an environment has been confirmed. Atmospheres themselves would face a long test. Without stellar ultraviolet radiation and a constant stream of stellar particles, some kinds of atmospheric loss might decrease, but cold gases could condense onto the ground. Nitrogen, oxygen, carbon dioxide, methane, and other compounds freeze at different temperatures and pressures, and what began as air could gradually become frost, snow, or deep deposits spread across the surface. The sequence would vary from planet to planet. On an Earth-like world, water would freeze before nitrogen and oxygen. Carbon dioxide could condense as temperatures fell. At lower temperatures, much of the remaining atmosphere could collapse onto the surface. Yet gases released by volcanism might continue to replenish it in small amounts. A world could pass through cycles in which an atmosphere forms, freezes, and later changes again as internal activity evolves. A companion moon could add another rhythm. If it survived the ejection, it would continue circling the planet, raising tides in any ocean and flexing the crust by small amounts. The pair would travel together around the galaxy, bound to one another, even after leaving the star that once defined their wider system. From the surface, the moon might be visible only when it passed in front of distant starlight, or when faint internal glow reflected from clouds and ice. Its phases would no longer be set by a sun. There would be no ordinary seasons to organize these changes. A rogue planet might still rotate, perhaps every few hours or every few days. It could have an axial tilt. It might retain moons and rings. But without a nearby star, rotation would not produce day and night in the usual sense, and orbital tilt would not create summer or winter. The passage of time would be measured by motion within the planet itself. Storms turning around a gas giant, ice shifting above an ocean, radioactive atoms changing inside rock, a moon crossing a sky with no bright center. This is where the word frozen can become misleading. A cold surface does not imply an inactive world. Beneath an exterior only a few degrees above absolute zero, pressure can build, minerals can change, and heat can continue moving. A rocky mantle may convect. A metallic core may remain partly liquid. A magnetic field might persist if conductive material inside the planet continues circulating. That field would no longer meet the wind of a parent star. Instead, it would move through the thinner mixture of charged particles and magnetic fields found between stars. Its shape and behavior would differ from the magnetospheres we know around planets in the solar system, but the interior process that creates it could continue. The surface above might hold no obvious sign. Imagine a plain of nitrogen frost under a sky with no sunrise. The ground gives off almost no visible light. Stars do not twinkle if there is no substantial atmosphere to disturb their paths, but they still fill the sky in every direction. The Milky Way would arch overhead, not as a bright painted band, but as the combined light of distant suns that do not belong to this world. There is no true midnight there, because midnight is a position relative to a star. There is only the planet turning. For human beings, warmth and light seem closely joined. A flame shines, the sun rises, and the air warms. Even a lamp announces itself by becoming visible. A rogue planet separates those ideas. Its most important energy may be hidden under kilometers of gas, rock, or ice, while its exterior remains almost entirely unlit. The heat below is not endless. Over immense spans of time, radioactive elements decay, interiors cool. Convection weakens. A gas giant contracts more gradually. A rocky planet may eventually lose much of its geological activity. The rate depends on mass and composition, and the final state may take far longer to approach than the lifetime of any civilization. Until then, the world carries a diminishing reserve from its formation. Every planet begins with energy stored by impacts, compression, chemical separation, and radioactive material. Around a star, that inner reservoir is easy to overlook because sunlight dominates the surface. In interstellar space, the proportions reverse. The faint heat below becomes the main continuing source. A wandering world is therefore not simply a planet after the lights have gone out. It is a planet learning to live on what it brought with it. To find a world without a star, astronomers often begin by watching stars. The method depends on patience rather than pursuit. A telescope surveys a crowded region of the sky, recording the brightness of millions of distant points. Most remain steady, some vary because the stars themselves pulse, flare, or pass behind dust, and on rare occasions, one brightens for a different reason. An unseen object has crossed the line between that star and Earth. The alignment does not need to be perfect in an ordinary sense. Gravity curves the path of light around mass, so rays that would have traveled past Earth can be redirected toward us. The background star appears brighter, even though it has produced no additional energy. This is gravitational microlensing. Maybe a star, a planet, a brown dwarf, or another compact object. It does not act like a glass lens with a solid surface. The bending happens in the space around it, where mass changes the geometry through which light moves. Because the lens is usually too distant and the separation too small, a telescope does not see a neat ring around the background star. It sees a temporary increase in brightness. The star rises above its normal level, reaches a peak, and fades as the alignment passes. The shape of that brightening carries information. A massive lens produces a wider region of influence, and usually a longer event. A star may create a signal lasting weeks or months. A planet can produce a much shorter change, sometimes measured in days, hours, or even less for very low masses. Duration alone does not reveal everything. The speed of the lens, its distance from Earth, and the distance of the background star also affect the event. A nearby fast-moving planet may produce a pattern resembling that of a more distant planet moving more gradually. Astronomers must often work with probabilities rather than a complete portrait of one object. Still, a short isolated signal can be powerful evidence. When a planet orbits a star, microlensing may reveal both bodies. The star produces the main brightening, while the planet adds a smaller disturbance to the curve. If only a brief planetary scale event appears, with no detectable stellar signature, the lens may be moving alone, or it may be orbiting so far from its star that the star's effect does not appear in the same observation. This uncertainty lies near the center of the search. A truly unbound planet and a planet on a very wide orbit can look similar during a short event. Additional measurements may help, but some candidates will remain unresolved. Astronomers therefore use careful language. They may describe an object as a free-floating planet candidate, an isolated planetary mass lens, or a likely unbound world. The words reflect what the data can support. The event confirms that mass crossed the line of sight. The more detailed history of that mass may still be hidden. Finding these events requires a sky dense with background stars. For that reason, surveys often watch toward the central regions of the Milky Way. In that direction, many stars overlap within a small patch of sky. Each one becomes a possible distant lamp whose light can reveal an intervening object. The galaxy's center is not visually simple. Dust obscures much of the visible light. Stars crowd together. Their images can blend on a detector. The same richness that makes the region useful also makes it difficult to measure. A survey must distinguish tiny changes in one star from the combined light of its neighbors. It must return to the same fields repeatedly. A single photograph is not enough. The important signal is change over time. Telescopes take image after image, building a record of brightness for each measurable star. Computer systems compare those records and identify unusual patterns. Possible microlensing events are then examined to see whether their shape matches the rise and fall expected from a gravitational lens. Many other things can imitate part of that behavior. A variable star can brighten. Two stars orbiting each other can eclipse and distort one another. Instrumental noise can create false changes. Weather can affect ground-based observations. Gaps between nights can hide the peak of a short event. A planetary signal may begin and end while the target region is below the horizon. This is why observing networks matter. Telescopes at different longitudes can hand the sky from one site to another as Earth turns. When night ends at one observatory, another farther west may still be able to continue. Several instruments watching the same field can fill gaps and confirm that a change occurred in the sky rather than inside one detector. For decades, this work has involved observers across continents, often concentrating on the months when the galactic center is best placed in the night sky. The search combines automation with human judgment. Software identifies candidates, alerts are distributed, and additional telescopes may begin watching the same star more frequently. The event itself does not wait. The lens, Earth, and background star continue moving. The geometry changes whether anyone is observing or not. Once the peak passes, the same alignment is unlikely to return. That makes microlensing different from many other forms of astronomy. A transiting planet circles its star and may cross again on a regular schedule. A radial velocity signal repeats with each orbit. A microlensing event is usually a single occurrence. Astronomers cannot simply wait for the lens to come back the following year. They must learn as much as possible from the light while it is changing. One useful approach is to observe from widely separated locations. Two observers do not see exactly the same alignment. Earth itself provides some separation between observatories, and a telescope in space can be much farther from a telescope on the ground. The difference in the observed light curve is called microlensing parallax. Parallax can help break some of the uncertainty between mass, distance, and speed. If two instruments see the event from different positions, the timing and shape may differ slightly. Those differences reveal more about the geometry. For short planetary events, the measurement is difficult. The signal may be faint, the timing narrow, and the necessary observations incomplete. But when enough information is gathered, astronomers can estimate the lens mass with far greater confidence. Another clue can come from the finite size of the background star. Simple descriptions treat a star as a point of light. Real stars have disks. If the lens passes across a line of sight close enough to resolve the effect of that disk through the changing magnification, the light curve may show subtle features. These can help determine the angular scale of the lensing event. Combined with other measurements, that scale may narrow the range of possible masses and distances. The planet itself may remain completely invisible. This can feel unfamiliar because most discoveries seem to begin with receiving something from the object. Light, radio waves, particles, or a reflected image. Microlensing can reveal a planet without detecting any radiation from the planet at all. The world is known through what its gravity does to light from somewhere else. In that sense, the background star is not the subject of the observation. It is the measuring instrument provided by the galaxy. Every suitable star marks a narrow path through space. A lens crossing that path alters the light for a short time. By watching enough stars for long enough, astronomers can begin to estimate how many unseen objects move between them. The challenge is statistical as well as observational. One detected event does not immediately reveal the total population. Astronomers must understand the survey's sensitivity. They ask how often the telescope was observing, how faint a star it could measure, which event, durations it might miss, and how efficiently its software could recover signals placed artificially into the data. Short events are especially easy to lose. A survey that checks a field once each night could completely miss a lensing event that lasts only a few hours. Even a faster survey may fail if clouds arrive at the wrong moment, or if the background star is too faint. The absence of detected low-mass planets does not necessarily mean the planets are absent. It may mean the observing rhythm was too slow. This relationship between cadence and discovery shapes the next generation of surveys. Astronomers want wide fields, sensitive detectors, stable imaging, and repeated observations separated by short intervals. A telescope above Earth's atmosphere can avoid weather, daylight, and much of the blurring caused by moving air. From space, crowded stellar fields can be measured with greater consistency. The goal is not merely to collect more candidates, it is to extend the search towards smaller masses and to distinguish isolated worlds from planets that remain attached to distant host stars. A survey capable of detecting brief lensing events could reveal planets comparable in mass to Mars, Earth, or perhaps smaller bodies under favorable conditions. It could show whether giant wandering planets dominate the population or whether the galaxy contains far more small rocky worlds that current observations rarely detect. The answer would reach beyond the isolated planets themselves. Every ejected world carries evidence about the planetary system that lost it. A large population of free-floating giants would suggest that violent gravitational rearrangement is common. A vast population of smaller bodies could reveal how efficiently young systems scatter planetary embryos, moons, and unfinished worlds. The empty spaces between stars may preserve the discarded pieces of planetary formation. Direct imaging offers another way to find some of them, though it favors a different population. Young planetary mass objects can remain warm enough to glow in infrared wavelengths. If one is nearby and sufficiently separated from bright stars, a telescope may record its own heat directly. These objects are often found in young stellar associations or star-forming regions where their age can be estimated from the surrounding population. Directly imaged objects provide spectra. Their light can reveal atmospheric molecules, cloud structure, temperature, gravity, and sometimes signs of changing weather. Astronomers may watch them rotate as brighter and darker regions move across view. Yet, direct imaging is best at finding young, warm, relatively massive bodies. An old Earth mass world crossing interstellar space would be far colder and fainter. It could pass near the solar system without becoming an obvious infrared source. For such objects, microlensing remains one of the few practical methods available. The two approaches, therefore, see different chapters of the same hidden population. Direct imaging finds some worlds while they still glow from formation. Microlensing can find them after their light has nearly disappeared. Between these methods lies a broad region of uncertainty. Objects may be too cold for direct imaging and too poorly aligned for lensing. They may travel through parts of the galaxy where background stars are sparse. They may exist in great numbers without ever producing a signal that reaches our instruments. This is not a failure of observation so much as a feature of geometry. A wandering planet does not announce itself. It must pass through the right line at the right time. While a telescope happens to be watching, for a few hours, a distant star becomes brighter. Then the alignment opens again. The world continues onward, unseen, but no longer entirely unknown. One brief brightening can reveal that a hidden world exists. A collection of such events can begin to reveal something larger. The galaxy may contain more wandering planets than visible stars, or it may contain fewer. It may be filled mostly with cold, rocky bodies, or its unbound population may be weighted toward larger worlds that are easier to detect. The answer remains uncertain because every method favors a different part of the population, and much of that population produces no detectable signal during the years we happen to be watching. A census of rogue planets is therefore not made by counting every object. It is built from samples. Astronomers record how many lensing events occur, how long those events last, and how sensitive the survey was to different masses and distances. They then use models of stellar motion, galactic structure, and telescope performance to estimate how many unseen planets would be needed to produce the observed pattern. The process resembles listening to rainfall from inside a building. You may not see every drop. Some strike the roof. Others fall beyond the windows. From the rhythm and intensity of what you can hear, you begin to infer the size of the storm outside. In microlensing surveys, the sound of the rain is replaced by changes in starlight. The shortest events are especially important because they may be produced by the lowest mass objects, but they are also the easiest to miss. A small planet creates a narrow lensing region. The alignment passes quickly, and the brightening may occur between scheduled observations. This creates a strong observational bias. Large lenses are easier to notice. Their events last longer, giving telescopes more opportunities to record the rise and fall. Small lenses move through their useful alignment before many surveys can collect enough measurements to recognize what happened. So, the worlds we detect are not necessarily the worlds that are most common. They are the worlds our instruments are best prepared to notice. The same principle appears throughout astronomy. Bright stars dominate the naked eye sky, even though faint red dwarfs are far more numerous. Large exoplanets were found before small ones, not because the galaxy lacked small planets, but because large planets produce stronger signals. Nearby galaxies were mapped before distant ones. The universe becomes populated in stages as observation reaches farther into what was previously hidden. Rogue planets may follow the same history. The earliest confirmed candidates naturally tended to be young, warm, or massive enough to leave a measurable trace. A cold body smaller than Earth would be much harder to find. It might pass across the sky for the entire age of human astronomy without reflecting enough light for any telescope to recognize it. Only an accidental alignment could reveal its gravity. When astronomers estimate the wider population, they must correct for all the ways a survey can fail to see an event. They simulate artificial brightenings and place them inside real observations. The analysis software is asked to recover them. Some are found, others disappear into noise, gaps, blending, or poor weather. From that recovery rate, the survey's efficiency can be measured. If a telescope detects 10 events of a certain type, but would have found only 1 out of every 10 that occurred, the true number passing through the observed region may be closer to 100. The exact calculation is more complex, but the underlying idea is simple. A count without an understanding of what was missed cannot describe the population. Distance adds another layer. A lensing event may be caused by a nearby low-mass object or a more distant higher-mass object. Its motion across the line of sight also changes the duration. Two very different worlds can create light curves that resemble each other. Astronomers build distributions rather than simple lists. They compare the observed events with many possible galactic populations. One model may contain large numbers of Earth mass wanderers. Another may contain fewer but more massive planets. Each model predicts a slightly different pattern of event durations and locations. As the sample grows, some models begin to fit better than others. This is one reason individual uncertainty does not prevent useful science. A particular event may never reveal the exact mass of its lens. Yet hundreds or thousands of events can still expose the shape of the hidden population. The galaxy does not need to introduce every world by name. Its statistics can speak for them. If small rogue planets prove abundant, they may represent the remains of planetary construction. Young systems probably create many more solid bodies than they retain. Some collide and merge, some fall toward their stars. Others are thrown outward before they can become full-sized planets. These unfinished worlds could range from large asteroids to bodies comparable with Mars or Earth. They may once have occupied crowded disks where dozens of planetary embryos competed for stable paths. A close encounter with a growing giant could send one outward. Another interaction could complete the ejection. The final planetary system would look clean and organized. The interstellar space around it would hold the evidence of everything removed. A high number of wandering giant planets would tell a somewhat different story. Gas giants require large amounts of material and usually form while the surrounding disk still contains gas. If many are later ejected, then unstable arrangements of massive planets may be common during the early evolution of stellar systems. A system can lose a giant while preserving smaller inner worlds. It can also lose smaller planets while the giant remains. The outcome depends on the masses, starting positions, and timing of each encounter. No single ejection history applies to every star. The rogue population is likely a mixture assembled through many routes. Some bodies may have formed in disks, some may have emerged directly from collapsing gas, some may have been freed when their stars passed close to other stars. Some may have been released when a binary system changed. A few could be removed much later, after a planetary system had seemed stable for billions of years. Stellar evolution can alter mass and gravitational balance. Passing stars can slowly disturb distant orbits. Galactic tides can weaken the hold of a star on objects already near the edge of its influence. The space between stars may therefore contain worlds of many ages. A young planetary mass object may still glow with formation heat and carry thick clouds through its atmosphere. Nearby, in the galactic sense, an older rocky body may have cooled beneath a shell of frozen gases. Another may be the surviving core of a planet stripped or altered during an encounter long ago. They would not look alike, even if all were called rogue planets. The name describes their present motion, not their composition. This diversity makes mass especially important. A body several times the mass of Jupiter may retain heat and atmosphere in ways a small rocky world cannot. A planet near Earth's mass may cool faster at the surface, but remain geologically active below. A body smaller than the Moon may lose heat quickly and resemble a large frozen fragment more than a familiar planet. There is no single experience of interstellar travel. Each world carries its own gravity, chemistry, rotation, moons, and interior history. The smallest bodies may be the most numerous because planet formation creates them in abundance. Building a planet is not a process in which every piece reaches completion. Disks begin with enormous numbers of grains and fragments. Only a fraction become large bodies. Of those, only some reach stable orbits. Nature often produces many starting forms and fewer survivors. The unseen population may preserve that imbalance. A galaxy with hundreds of billions of stars has had billions of years to scatter a material. Even if each planetary system released only a few substantial bodies, the total would become immense. If young systems commonly eject dozens of smaller worlds, then interstellar space could contain a much larger planetary population than the orderly systems around stars suggest. Yet large numbers do not mean crowding. The Milky Way is wide and deep. 1 trillion wandering planets spread through its disk would still be separated by great distances. Most would never pass near another planet. Many would travel for billions of years without entering a stellar system. A chance captures is possible, but difficult. For one star to capture a passing planet, energy must be removed from the encounter. A simple two-body meeting usually leaves the planet with enough speed to depart again. A third object, such as another star or planet, can change the exchange and allow capture under suitable conditions. Young clusters may provide more opportunities because stars are closer together and interactions are more frequent. A rogue planet could enter a new system and remain there. Its new orbit might be distant, tilted, or highly elongated, preserving signs that it did not form alongside the system's other planets. Some unusual worlds around stars may have been captured. Although demonstrating such an origin is difficult, a planet can therefore have more than one astronomical home. It may form around one star, travel through interstellar space, and eventually orbit another. Its chemistry would record one birthplace, while its motion reflects a later encounter. Other wanderers may never belong to a star at all. The distinction between a captured planet and an object formed directly from a cloud may remain hidden unless precise information about age, composition, and motion can be gathered. For distant objects, those clues are rarely complete. Astronomers must reconstruct history from the present state. That reconstruction becomes more reliable when many objects are studied together. Motions can reveal whether a group shares an origin. Atmospheric measurements can show whether young free-floating bodies resemble giant planets around stars. Lensing statistics can reach colder masses that emit too little radiation for direct study. Each method supplies a different piece. Direct imaging provides light but favors youth and warmth. Microlensing provides gravity but often only once. Wide field surveys provide numbers but require careful modeling. No single telescope will uncover every wandering world. The census will emerge from overlapping searches, repeated observations, and years of comparison between what was detected and what remained beyond reach. From where you are resting now, the night sky may seem organized around stars. They mark constellations, they illuminate dust. They define the visible structure of the galaxy. A planet without a sun contributes nothing obvious to that pattern. But between those points of light, mass continues moving. The darkness is not an empty background placed behind the stars. It is a region crossed by planets, comets, fragments, and cold bodies, whose presence becomes apparent only when gravity briefly rearranges the light beyond them. Their number will tell us how planetary systems grow by losing things. Every stable orbit may have a history of discarded alternatives. Every mature system may be surrounded, far beyond its remaining planets, by paths that began there and never returned. The worlds between the stars are not exceptions to planetary formation. They may be one of its most common results. There is another possibility beneath the frozen surface, one that cannot be judged by darkness alone. A world without sunlight may still contain places where energy moves from one form into another. Heat can rise through rock. Water can circulate through fractures. Minerals can react with dissolved gases. A moon can pull rhythmically on a planet, or a planet on a moon, bending an interior and turning orbital motion into warmth. None of this means that a wandering world is inhabited. It means only that the absence of a star does not remove every condition that life might use. On Earth, sunlight supports most of the living surface. Plants, algae, and certain microbes capture radiant energy, and the chemistry they build spreads through oceans, soil, and atmosphere. Even many organisms that never see the sun depend indirectly on material produced in illuminated places. But not every ecosystem begins with light. At hydrothermal vents on the ocean floor, seawater enters cracks in the crust, meets hot rock, and returns carrying dissolved minerals. Microorganisms can use chemical reactions involving substances such as hydrogen, sulfur compounds, methane, and carbon dioxide. They form the base of communities living far below the reach of daylight. These environments changed how scientists thought about habitability. They showed that life can use a chemical gradient rather than a beam of sunlight. Warm fluid meets cold ocean water. Reduced compounds from rock encounter more oxidized surroundings, and the difference provides usable energy. A rogue planet with a buried ocean might contain similar boundaries. Water could touch a rocky seafloor. Heat from radioactive decay and the slow cooling of the interior could drive circulation. Reactions between water and certain minerals might produce hydrogen. If carbon-bearing compounds and other necessary elements were present, the ocean could hold a continuing network of chemical possibilities. Whether those possibilities would be sufficient is unknown. Earth offers only one example of a living planet, and all known life shares a common biochemical history. We do not yet know which features of that history are universal and which belong only to this world. Liquid water is useful because it dissolves many substances and allows molecules to move, meet, separate, and react. Carbon can form complex structures. Hydrogen, nitrogen, oxygen, phosphorus, and sulfur play central roles in terrestrial biology. Yet ingredients alone do not make a living system. Life also needs disequilibrium. There must be differences that have not already been erased. Hot and cold, acidic and alkaline, reduced and oxidized, concentrated and dilute. A completely uniform ocean at chemical balance would offer little free energy for metabolism. This is contact between water and rock matters. The seafloor is not merely the bottom of an ocean. It can be a chemical engine. Fresh rock exposes minerals. Fractures create pathways. Heat moves fluid through pores. Reactions alter the crust and release new compounds into the water. On a geologically active rogue planet, those exchanges might continue for immense spans of time. The rate would depend on the planet's mass, age, composition, and internal structure. A small world could cool until circulation weakened. A larger rocky world might preserve mantle activity longer. Too much water could create another problem. At great pressure, unfamiliar forms of ice can develop beneath the liquid layer. Ice is usually imagined floating above an ocean. Under enormous pressure, some crystalline phases of ice become denser than liquid water. On a water-rich planet, such ice could form at the bottom of the ocean, separating liquid water from the rocky mantle. That barrier might reduce the direct exchange of minerals and chemical energy between rock and sea. A hidden ocean could therefore exist and still be poorly connected to the ingredients beneath it. The thickness of the water layer matters as much as its presence. A more Earth-like amount of water could allow the ocean to rest directly on rock. A much deeper global ocean might produce high-pressure ice along the sea floor. Heat could still pass upward, and some exchange might occur through cracks or melting. But the environment would differ from known hydrothermal systems. The surface shell creates its own separation. Kilometers of ordinary ice could protect an ocean from the cold of interstellar space. The lower surface of that shell might melt and freeze as heat flow changed. Salts could be pushed through the ice or trapped within it. Slow convection might carry material between layers. Without a nearby star, however, the upper surface would supply little photochemical energy. On worlds orbiting stars, ultraviolet radiation can create reactive compounds in an atmosphere or on ice. Those products may later move into an ocean. A rogue world would receive only the weaker radiation of interstellar space, cosmic rays, and passing starlight. Its chemistry would rely more heavily on internal processes. This could make life less productive, even if it remained possible. An ecosystem powered by a limited geothermal supply might support far less biomass than Earth's sunlit surface. It could be confined to cracks, vent fields, or thin regions where fluids mix. Long distances of ocean might contain almost no life at all. There is no reason to imagine forests beneath the ice. The more scientifically careful picture is smaller. Films of cells on mineral surfaces, communities inside warm pores, or organisms moving through water near a source of chemical energy. Even these images are extrapolations from Earth, not observations of another world. A thick hydrogen atmosphere offers a different route. Hydrogen molecules can absorb infrared radiation through collisions, allowing a sufficiently dense atmosphere to slow the loss of internal heat. Models suggest that a rocky planet with enough hydrogen could maintain liquid water at or near its surface without starlight. Such a world would not resemble Earth under a black sky. Its atmospheric pressure could be high. The air might extend far above the surface. Clouds, hazes, and condensed materials would depend on temperature and composition. Internal heat would rise from below, then move through the atmosphere before escaping to space. The conditions required may be difficult to preserve. A planet must acquire the hydrogen, retain it through formation and ejection, and avoid losing too much over time. Its internal heat must fall within a useful range. Too little, and water freezes deeply. Too much, and surface conditions could become hostile to the chemistry being considered. The idea remains valuable because it widens the meaning of a habitable zone. Around a star, the traditional habitable zone describes distances where a planet with suitable conditions might maintain liquid water on its surface. A free-floating world has no orbital distance to place inside such band. Its habitable region, if one exists, is defined inward. It may lie beneath ice, within an atmosphere, beside a vent, or inside the porous boundary where water meets stone. A wandering giant planet could carry another set of possible habitats through its moons. If a moon survives ejection, the planet's gravity can continue to raise tides inside it. A perfectly circular orbit eventually reduces this flexing, but interactions with other moons can maintain orbital eccentricity. As the moon moves closer and farther during each orbit, its interior bends and releases heat. This is the mechanism that helps warm several moons in our own solar system. Around a rogue giant, tidal heating would not require sunlight. A moon with water, rock, and a suitable orbit could retain a buried ocean. Under some modeled conditions, an atmosphere and continued tides might allow liquid water nearer the surface for long periods. Again, survival is not guaranteed. The violence that ejects a planet can remove moons, rearrange their orbits, or cause collisions. Some satellites may remain bound. Others may be left behind with the star or released as independent wanderers. A planet and moon that escape together carry a small gravitational system into interstellar space. The planet becomes their central body. The moon continues through phases of position, though not phases of illumination. Tides rise and fall in a concealed ocean. Orbital energy slowly becomes heat. The pair may travel through the galaxy long after the system that formed them has dispersed. From outside, almost none of this would be visible. A cold ice shell might reveal no ocean. A dense atmosphere could hide the surface. A microlensing event might provide only a mass estimate and no information about chemistry. Direct imaging of a young object might reveal clouds and temperature, but not a buried sea. The most important features could remain inaccessible. This creates a deep observational problem. Habitability is already difficult to evaluate on planets orbiting stars, where atmospheres can sometimes be studied as they absorb or emit light. For a rogue world, the usual source of illumination is missing. A nearby warm giant might be examined in infrared wavelengths. Its spectrum could reveal water vapor, methane, carbon monoxide, ammonia, clouds, and other atmospheric features. But a cold, rocky planet with a subsurface ocean might offer no detectable sign of the liquid water below. It could be biologically inactive. It could support chemistry for billions of years. From Earth, both states might look the same. The uncertainty should not be filled in either direction. Darkness is not evidence of life, nor evidence against every possible habitat. It simply changes where the search must be imagined and what kind of energy must be counted. For a world around a star, attention naturally turns outward, toward the light arriving from above. For a wandering planet, the important direction may be down, below frozen gases, below ordinary ice, below water under pressure. A boundary between ocean and rock could continue exchanging heat and matter. No sunrise would reach it, no season would alter it. Its timescale would be set by cooling stone, decaying elements, and the gradual evolution of an unseen interior. If life ever began there, it might never know that stars exist. Once a planet has left its star, the galaxy becomes its larger orbit. It does not move in a straight line forever. The Milky Way's gravity bends every path, including those of stars, gas clouds, clusters, and worlds that no longer belong to a solar system. A rogue planet joins that shared motion, traveling around the galactic center, while rising above and falling below the galaxy's broad disk. Its former star may continue on a similar path for a time. If the planet was released at a moderate speed, both objects still carry much of the motion they had before separation. They may drift apart gradually, remaining in the same region of the galaxy for millions of years, but small differences accumulate: spiral structure, nearby stars, and the galaxy's wider gravitational field alter their paths. Eventually, the distance becomes too large for any practical connection to remain. The planet's birthplace disappears into the stellar background. There is no trail through space, marking where it came from. No wake remains behind it, unless astronomers could reconstruct its position and velocity with remarkable precision. Then compare those measurements with the motions of many stars over long intervals. Its origin would be lost. For a young object, that task may still be possible. Members of a newly formed stellar association often move together through the galaxy. Their shared direction reveals that they emerged from the same cloud, even after the original cluster has begun to spread apart. A free-floating planetary mass object. Traveling with them may belong to the same generation. For an older world, the evidence grows faint. After several journeys around the Milky Way, a planet may have passed through, changing neighborhoods of stars and gas. Its motion has been disturbed by many weak encounters. The cloud that formed its system may no longer exist. The stars once born beside it may now be scattered across thousands of light years. The planet continues without a memory that can be read from its path alone. Its speed depends partly on how it was released. A planet gently unbound from a distant orbit may leave its star with only a modest difference in velocity. A powerful interaction among giant planets can send a world away faster. A close stellar encounter can add another gravitational push. In rare circumstances, a planet may be accelerated enough to move very differently from the stars around it. Even then, most wandering planets remain citizens of the galaxy. The Milky Way's gravity holds far more strongly than the gravity of any single star. Leaving a solar system is relatively easy compared with leaving the galaxy itself. A world can become unbound from its sun, while remaining bound to the enormous distribution of mass surrounding the galactic center. Its year becomes a galactic year. For the Sun, one circuit around the Milky Way takes roughly a few 100 million Earth years. A rogue planet traveling through a similar region would move on a comparable timescale, though its exact orbit could be more elongated or more tilted than ours. During one such circuit, entire species can appear and vanish on Earth. Continents can open and close. Mountain ranges can rise, erode, and return to sediment. For the wandering planet, a single passage around the galaxy may be only another interval in its cooling history. Along the way, it crosses environments that differ greatly from one another. Some regions contain more stars, others are sparse. Molecular clouds gather cold gas and dust into broad structures where new stars may eventually form. Supernova remnants expand and thin. Magnetic fields thread the space between systems. High-energy particles move through the galaxy from distant sources. Most of these surroundings would barely disturb a massive planet. Interstellar gas is exceedingly thin compared with a planetary atmosphere. Even inside a molecular cloud, the density is low by terrestrial standards. A rogue world passing through such a region would not feel a wind like weather on Earth. Over millions of years, however, small effects can accumulate. A planet with a magnetic field would interact with charged particles. A world with a tenuous atmosphere might collect some material and lose some through other processes. Dust grains would strike the surface or upper atmosphere at high speed. Cosmic rays would continue altering exposed ice and molecules. The planet would not remain chemically untouched. On an airless surface, energetic particles could break molecular bonds and create new compounds in the uppermost layers. Ice could darken or change texture. Buried material would remain better protected, preserving older chemistry beneath the altered surface. If the planet carried a thick atmosphere, that atmosphere would absorb much of the incoming radiation. High above the deeper clouds, molecules could be split apart and recombined. Hazes might form. The upper atmosphere could evolve even while the lower layers were shaped mainly by heat rising from within. The galaxy supplies no regular climate, but it does provide changing surroundings. A passage near a star would be one of the more noticeable events. Most stellar encounters would remain very distant. The spaces between stars are so large that a rogue planet could travel for billions of years without passing close enough to enter another planetary system. When a nearer approach did occur, the star would gradually brighten. At first, it would be only another point. Over thousands of years, it might become the dominant object in the sky. For a frozen surface, even a close stellar passage would probably be too brief to create a lasting temperate climate, but the additional energy could change the outer layers. Frozen gases might begin to sublime. An atmosphere could temporarily thicken. Surface ice could crack as temperatures shifted. If the planet passed near enough, sunlight might reach a buried layer, indirectly through warming and melting near the top. Then the encounter would end. The star would recede, the surface would cool again, and condensed gases might return to the ground. A planet could experience several such episodes across its lifetime, each one separated by intervals longer than the history of human civilization. Most would leave only subtle geological records. A close stellar passage also changes motion. The star's gravity bends the planet's trajectory. Usually, the planet approaches and departs along a new direction while remaining unbound. Its speed relative to the star changes temporarily, then settles into a different galactic path. Capture requires something more. In a simple encounter between one star and one planet, gravity accelerates the planet inward and slows it by the same amount as it leaves. Without another interaction, there is no easy way for the planet to lose enough energy to remain. A third body can change that balance. If the star has a companion, or if the encounter occurs within a crowded young cluster, energy can be exchanged among several objects. One body may leave faster while another becomes bound. A rogue planet can, under suitable conditions, be captured into orbit. The new orbit may be unlike those of planets formed with the star. It could be steeply tilted. It could move backward compared with the system's original planet. It might travel on a long ellipse, spending most of its time far away, and returning only occasionally to the inner regions. Such an orbit would carry a history of arrival, yet proving capture would be difficult. Planetary systems can develop unusual orbits through their own internal interactions. A distant tilted planet is not automatically an adopted world. Composition could provide another clue. A captured planet formed around a different star might contain chemical proportions unlike those of the new system. But reading that difference requires observations precise enough to compare atmospheres, interiors, and formation histories across great distances. The identity of an adopted planet may remain hidden even after capture. It would have a sun again, but not its first one. For some worlds, capture might restore cycles of illumination. A distant orbit could create long seasons measured in centuries or millennia. A closer orbit might warm frozen gases and reshape the atmosphere. If oceans remained beneath ice, increased surface energy could alter the shell above them. The result would depend on how long the planet had wandered. A young world might still possess a thick atmosphere and active interior. An older one may have lost much of its accessible gas to the surface. A planet arriving after billions of years in deep cold would not simply return to its original state when sunlight appeared. Ice would expand and contract. Deposits would melt in sequence. Gases would enter the atmosphere at different temperatures. Old chemical layers, preserved through the interstellar journey, could be exposed again. Capture could create a second planetary history built upon the first. Other planets would never meet another star closely enough to change their condition. They would continue around the galaxy as isolated bodies, passing through one spiral region after another. The Milky Way's spiral arms are not rigid structures carrying the same stars forever. They are patterns of density through which stars and planets can move. A wandering world may enter a region where gas is compressed and star formation is more active, then later return to a less crowded part of the disk. Nearby supernovae would remain rare, but over billions of years, some planets may pass within distances where radiation affects their atmospheres or surfaces. A world with no atmosphere would receive that energy directly. A buried ocean would remain shielded, by ice and rock. The same isolation that removes sunlight can also provide protection. Thick outer layers can separate an interior from briefer events in the surrounding galaxy. A subsurface environment, if present, may be governed more by internal heat than by what happens among the stars above it. The surface travels through changing cosmic weather. The deeper world follows its own clock. There is a human habit of thinking about planets as destinations fixed beside particular suns. Mars belongs near our star. Jupiter belongs farther out. Exoplanets are introduced through the names of the stars they circle. A rogue planet has no such address. Its location is temporary. Its nearest star changes. Its path crosses the boundaries. People draw between constellations. Over long periods, even the shape of the constellations changes while the planet continues beneath them. It belongs not to a star, but to motion. And through the galaxy's turning disk, that motion can continue long after every trace of its first sky has disappeared. The next great change in this search will not come from a brighter view of the planets themselves. Will come from watching more stars with greater precision. The Nancy Grace Roman Space Telescope was designed with that kind of patience built into it. From its position near the second Sun-Earth Lagrange point, roughly 1 million miles from Earth, Roman will observe fields of the inner Milky Way in infrared light. Its wide-field instrument can return again and again to regions crowded with stars, building the steady record that microlensing requires. Roman is expected to monitor tens of millions of stars over hundreds of days. Most of those stars will never brighten through lensing while the telescope is looking. Some will. Among those brief changes may be the signatures of planets still bound to distant suns, worlds on wide orbits beyond the reach of many other techniques, and isolated masses crossing the galaxy without a host star close enough to reveal itself. The importance of Roman is not only the number of planets it may find, it is the consistency of the survey. A telescope in space does not lose the galactic center to passing clouds. Its images are not blurred by moving air. Its detectors can measure crowded star fields with a stability that is difficult to maintain from the ground. Repeated observations can be scheduled at the cadence needed to catch events that rise and fade quickly. That cadence opens the search toward lower mass. A planet comparable with Jupiter may create a lensing event lasting long enough to be sampled many times. An Earth-mass world produces a shorter signal. A body smaller than Mars may offer only a narrow interval during which the alignment is useful. To recognize such a world, the telescope must already be watching. Roman was built to make repeated attention possible. The result may be the first census of planets outside the familiar picture of a solar system. It may reveal whether free-floating giant planets are rare products of unusually unstable systems or common outcomes of planetary formation. It may show whether Earth-mass wanderers exist in greater numbers than gas giants, as some models predict. And it may expose a population below that scale, where the word planet begins to meet the unfinished material from which planets are made. Microlensing does not care whether a body has an atmosphere, a crust, or a name. It responds to mass. A dark object can be old or young, rocky or gaseous. If its gravity bends the light of a background star strongly enough, it enters the survey. This gives Roman access to a part of planetary history that other methods often miss. Transit searches favor worlds that pass repeatedly in front of their stars. Radial velocity surveys favor planets whose gravity produces a detectable stellar wobble. Direct imaging favors bodies that remain warm, bright, and widely separated from a star. Roman's microlensing survey will favor alignment. For a short time, the galaxy places one object behind another, and the hidden mass becomes measurable. Ground-based observatories will still matter. They can watch the same regions from another position and compare measurements made from Earth with those made far away in space. The separation between observers creates parallax, allowing astronomers to estimate the geometry of some events more precisely. For certain lenses, that difference may help determine mass rather than merely suggest it. A brief brightening could become a measured planet. Even then, some events will remain incomplete, and some planets will be impossible to distinguish from bodies on very wide orbits. The survey will not remove uncertainty. It will give uncertainty a much larger sample. That may be enough to change how planetary systems are understood. For a long time, the planets around our Sun provided the only example available. Their nearly shared plane, mostly orderly orbits, and clear attachment to one central star made a planetary system seem like a stable arrangement. The discovery of exoplanets widened that picture. Giant worlds appeared close to their stars. Multiple planets were found in compact orbits. Worlds circled binary stars. Some systems seemed crowded, tilted, or shaped by migration. Rogue planets widen the picture again. They suggest that a planetary system cannot always be defined only by what remains around the star. Its history includes what was removed. A mature star may traverse several planets in calm orbits while carrying no obvious record of the worlds that once moved among them. Those lost bodies could now be thousands of light years away, crossing unrelated constellations and bending the light of stars that formed long after their departure. To count them is to study absence through consequence. Each isolated lensing event becomes a fragment of a system we may never identify. No image shows the original encounter. No observation reveals the last orbit before escape. Yet the planet's mass, motion, and frequency can still tell us something about how often young systems become unstable. A large population of wandering worlds would mean that loss is not a rare accident at the edge of planet formation. It is one of the process's ordinary tools. Systems settle because some bodies collide, some migrate, and some leave. There is a generational thread in the way this knowledge has been built. Early observers recorded the changing brightness of stars by eye. Photographic plates preserved faint fields across decades. Electronic detectors made small variations easier to measure. Wide-field surveys began watching millions of stars at once. Networks of astronomers learned to respond when one distant point brightened in the pattern expected from lensing. Now a space telescope will continue that work from beyond Earth, returning to the same crowded regions with a wider and steadier view. No single observer will watch a rogue planet cross the detector. The event will be assembled through instruments, software, archives, and teams spread across time. Someone may design the survey years before the light arrives. Another person may maintain the telescope. Others may identify the curve, test alternative explanations, and compare it with thousands of events that came before. The planet itself may have been traveling alone for billions of years. Its discovery will be communal. Future infrared observatories may add another layer by detecting the heat of nearby young wanderers. Extremely large, ground-based telescopes may obtain finer spectra of free-floating planetary mass objects, revealing clouds, rotation, and atmospheric chemistry. More precise astrometry may trace the motions of nearby candidates and connect some of them to young stellar groups. A very close rogue planet might someday be found by more than one method. Its infrared glow could reveal temperature. Its motion could reveal distance. Microlensing could reveal mass. Together, those measurements could turn a hidden lens into a physical world with weather, gravity, and a history that can be modeled. Such a discovery would still not make the planet easy to reach. Even a nearby wanderer could lie far beyond the practical range of present spacecraft. But distance does not remove scientific intimacy. We know stars we will never visit by the light they send. We study black holes through the motion and radiation around them. We reconstruct the early universe from traces preserved in the sky. A wandering planet asks for the same kind of patience. It may give us only a pulse of magnified starlight or a faint infrared spectrum shaped by clouds too distant to see. From those small signals, a larger history can emerge. The coming census may not reveal one typical rogue world. It may reveal that there is no typical one. Some will be heavy enough to resemble the boundary between planets and brown dwarfs. Some will be rocky bodies close to Earth in mass. Others may be smaller remnants of interrupted formation. Their temperatures, atmospheres, moons, and internal activity will differ because their beginnings and journeys differ. What unites them is not appearance, it is release. They have crossed beyond the gravitational claim of a star and entered the larger architecture of the galaxy. As Roman and later surveys watch the Milky Way's crowded center, many of these worlds will remain unseen. Their paths will never align with a suitable background star during the years of observation, but a fraction will pass through. The narrow geometry required. A distant point will brighten. The curve will rise, turn, and settle. And for that brief interval, a planet with no sunrise will cast its gravity across the light. A world without a sun does not know that it has been lost. It continues under gravity, carrying whatever it retained from the system that formed it. A core may remain warm. An ocean may endure beneath ice. A moon may circle overhead. Storms may turn through a deep atmosphere, driven not by daylight, but by heat rising from below. There is no moment when the planet understands that the sky has changed. Only matter responds. Gases condense, water freezes, orbits widen and break. Radiation escapes, rock cools. The motions continue without judgment, each one following the same physical laws that guide planets beside stars. From Earth, we give these bodies names that reflect our own position. We call them orphaned, free-floating, unbound, or rogue. Each word begins with the idea of a home that is no longer present. But a planet is not defined only by what it circles. It is also a structure held together by its own gravity, a record of pressure, collision, chemistry, and time. It may contain layers older than its wandering. It may carry isotopes formed before its first star began to shine. Its surface may preserve the moment when the last warmth of that star faded into the ordinary light of the galaxy. The planet does not become less real when it becomes difficult to see. Its mass remains. Its interior continues to change. Its path is written into the larger motion of the Milky Way. Perhaps this is the most important thing these worlds offer. They make visible, for a few measured hours, how much of the universe exists outside the arrangements that are easiest for us to recognize. A solar system is clear because light gathers attention toward its center. A star illuminates its planets, marks their years, and reveals their atmospheres. The system appears complete because we can see what remains within it. The wandering planets tell another part of the story. Formation creates more possibilities than stability preserves. Young systems rearrange themselves. Some bodies remain close, some move outward, some collide, some fall inward. Some cross the final boundary and never return. The space between stars receives them all without ceremony. There may be no explosion when a planet leaves. No visible line marks the edge of the system. The star simply becomes weaker in the sky as the planet moves farther away until it joins the other distant lights. Then the long cooling begins. For a giant planet, that cooling may take longer than the present age of the universe. Heat can remain trapped beneath thick layers of gas, leaking outward at a rate too faint for human sight. Clouds may continue to circulate. Chemistry may continue in the pressure below. For a rocky world, the surface may become sealed beneath frozen atmosphere and ice. Farther down, water may remain liquid where pressure and internal heat allow it. Minerals may react along the seafloor. A metallic core may turn beneath the mantle. None of these possibilities can be assumed for every world. Some planets will be inactive and frozen nearly through. Some will be too small to preserve much internal warmth. Some will be torn apart before they ever leave their systems. Others may retain complicated interiors for billions of years. The category contains not one kind of planet, but many kinds of departure. Our observations will gradually separate them. A short lensing event may suggest a low-mass world. A longer one may reveal a heavier body. Infrared light may identify a young object still warm from formation. Motion through a stellar association may connect it to a shared birthplace. Each measurement removes a small amount of uncertainty, yet even the best future survey will leave most wandering planets unknown. The geometry required for microlensing is narrow. A planet must pass close to the line between Earth and a distant star while a telescope is watching. Countless will move through other parts of the galaxy, never crossing a useful alignment during the entire span of human observation. Their absence from our records will not mean they are rare. It will mean their gravity never entered the right line of light. There is a certain calm in that limitation. The galaxy does not arrange itself for complete understanding. It offers brief alignments, partial views, and traces that must be gathered across generations. Some questions become clearer. Others widen as the instruments improve. A planet passes, a star brightens, the event ends. Years later, its curve remains in an archive where another observer may compare it with new models and see more than the first analysis could reveal. In this way, even a one-time event can continue producing knowledge after the planet itself has traveled far beyond the position where it was detected. The light returns to normal, but the information remains. Long before telescopes could measure such changes, people already understood the night through fixed stars. Those stars provided direction because they appeared reliable. They rose in known places. Their patterns returned with the seasons. The discovery of wandering planets does not make that older sky less dependable. It adds another layer behind it. Between the familiar points are bodies that do not announce themselves. They cross the same galaxy as the stars, but belong to no visible pattern. Their paths cannot be traced into constellations. Their years cannot be counted by sunrise. Still they move with order. They follow curves shaped by mass. They exchange heat according to the same laws that govern Earth. They preserve chemistry according to the materials they contain. The darkness around them is not outside nature. It is one of the conditions nature allows. And here, beneath the star that still rises, each morning, it is possible to think of those distant worlds without turning them into symbols of loneliness. They are not waiting to be found. They are not searching for another sun. They are simply continuing. A frozen atmosphere may rest across a plain. No light has touched for millions of years. Beneath it, rock may hold a little warmth. Far above, the galaxy may stretch across the sky as a broad field of distant suns. The planet turns under them. No day begins, no evening arrives. A moon, if one remains, completes another orbit. A current moves beneath ice. A storm crosses the upper clouds of a giant world, invisible except for the heat it carries. Time passes there without brightness, and elsewhere in the galaxy, another young system is forming. Dust circles a star. Planetary bodies grow, migrate, and disturb one another. One of them may already be moving toward an unstable path. Millions of years from now, it may leave. It may carry an atmosphere, oceans, rings, or moons into the space beyond its star. It may travel through the Milky Way for longer than that star will live. Perhaps one day, its gravity will bend the light of a distant sun toward a telescope not yet built. For a few hours, it will be present in our measurements. Then, the alignment will open, the star will dim to its ordinary brightness, and the planet will pass on. The unseen world keeps its course.